The heat of vaporization, I think we talked about delta H vap. Okay, the heat of vaporization, that is basically the energy required to make a substance, usually a gram or a mole, go from a liquid to a gas. Okay, so heat of vaporization. So again, if you have stronger or more bonds, what sort of thing you're going to see through heat of vaporization? If you have stronger bonds, is it going to be higher or lower as far as the amount of heat you need for it to go from a liquid to a gas? Higher. Mm-hmm. Does that make sense? Yeah, that's just it. Delta H vap. I mention that because the Clausius Clapeyron equation actually is a way to look at the equilibrium vapor pressure of a substance at a particular temperature, and actually that's kind of a volatility issue. Okay, the more volatile the substance, the higher the equilibrium vapor pressure is at a particular temperature, the more volatile substances. So it links that to, for that same substance, the heat of vaporization for that substance. So there's the Clausius Clapeyron equation, which I handed you out. It's the second one on there, Clausius Clapeyron equation. And from that equation, you make what's called a Clausius Clapeyron plot. From here on out, if you hear me say CC, that means Clausius Clapeyron. Okay? Just simply a CC equation. Okay, and from your CC equation, you make a CC plot. Okay? Because that's a mouthful. So the heat of vaporization, the delta H vap, heat of vaporization, how much energy you need to make to probably jack into a gram in order for it to go from a liquid to a gas. That actually, for some substances, will vary with temperature, but for some substances, to kind of whatever temperature the liquid is, it still takes the same amount of energy to go ahead and vaporize. So for those substances, we can make a plot, a CC plot, a Clausius Clapeyron plot. Now, as the investigator, and actually on Thursday, I hope you're going to remember all this from Friday to next Thursday's lab, because Thursday you actually are going to gather data to make a Clausius Clapeyron plot. So the data that the investigator gathers, what does P stand for?
Vapor pressure?
Pressure, vapor pressure. Very good. Yeah, that's what P stands for. And what does T stand for? Temperature. Yep. So those are the two things that you'll have control over. Notice that we can't go with just pressure, but the CC equation, Clausius Clapeyron equation. I was thinking pickles right now. That it actually links the natural log of pressure. So one of the things, and I don't know if you have your calculators here, but I'll be kind of playing with your calculators maybe a little bit to find your LN key. That's the natural log of pressure. Delta H vap, that is for the substance that you're looking at the two, the equilibrium vapor pressure and the temperature of. Just one substance has one heat of vaporization. Of course, R, what's R? Ideal gas law constant, exactly. And actually, I'm going to tell you we're going to use a slightly different version. I think we're going to use the thermodynamic version of R. Remember, there's kind of two different versions of R. Okay, the C here, don't worry too much about it. It's just kind of it's a throwaway kind of constant, so don't worry too much about it. All right. Oh, and also there you saw that the temperature needs to be, it can't be in Celsius, even though Celsius is metric, it has to be in units of Kelvin, temperature units of Kelvin. All right. So do you see how this is very similar to the Clausius Clapeyron plot? Or excuse me, equation I gave you. The thing that this does is it kind of pulls out that temperature term. That's the only difference. The reason being that the temperature is what we're going to focus on, but it's like what we call the inverse of the temperature. 1 over T is what we call the inverse of temperature. We do this a lot in physical science. Okay, we kind of look for a relationship like the Clausius Clapeyron equation, and then we look for a way to plot that relationship. And so if we kind of pull out the 1 over the t or the 1 over t term, okay, we are actually going to plot that on the x-axis. What I'm creating over here is your first look at the plot, the CC plot that comes from the CC equation. So we plot what's called the inverse of temperature, 1 over t here. And then along the y-axis, we will be plotting the natural log of your equilibrium vapor pressure, the natural log of your pressures. These, I'll just go ahead and tell you, are you guys familiar with a negative slope, what a negative slope looks like? Good. If you're not, or if you are, that is a negative slope. These will have a negative slope. Okay. There should be a straight line if you gathered your data right. And the cool thing about this was done on purpose, is that the slope of that line, which we use the variable m for slope, the slope of that line is going to be equal to the heat of vaporization for that stuff over r times -1, actually. Okay, so over here, I'm going to go ahead and I'll say m, the slope of this line, this Clausius Clapeyron plot line, is equal to negative delta H heat of vaporization for that substance divided by a constant. Okay, so that's it in a nutshell. Let's see. Okay, here are several substances on the same graph. Okay, so these are independent Clausius Clapeyron plots of substances. And I've gone ahead and brought in the structures that we had earlier. We looked at, what did we look at? We looked at, we looked at benzene, but it was like a vapor pressure curve before, the same substances. So aniline, yes, is a benzene with one of the hydrogens is kicked off and replaced by an aniline group, or an amine group. Okay? So let's see, they ran it 1, 2, 3, 4. They ran it 5 times because there's 5 dots up there. They took their pressure and took the natural log of it. They took their temperatures and made sure it was in Kelvin, and then took the 1 over that temperature, and they plotted those. That's it. That's for aniline. Okay, and here are the other substances. Kind of from left to right, toluene is benzene with a methyl group. Water is the black line. Benzene is the blue line, and diethyl ether is the red line. Okay. So actually we're going to be, I think in the next slide, we're going to be picking on benzene. So these are all Clausius Clapeyron plots. So if we pick on benzene and we use the previous thing, okay, we could answer this question. What is the temperature in Kelvin needed for benzene to have an equilibrium vapor pressure of 116 millimeters of mercury? Now, right away, you run into the situation where pressure here is in 116 millimeters of mercury, but on our plot, we have the natural log of pressure. So that's fine. The first thing actually we're going to do is take the natural log of 116. And Matthew's getting his phone out. Take the natural log of 116. You can practice. I brought mine to practice. We haven't used the natural log key. That work? Okay, so now 4.75 we can find on our graph. Okay, so if you find 4.75 on the graph, okay, it will come, it's right here. Okay, so we look at benzene and we drop down to see where it hits the inverse of temperature, which is a value of 3.3. Okay, so 4.75 was the natural log of 116. Where it intersects our line is 3.3. Now, aside, I have to tell you, this is one of my, how you set up your scale down here doesn't have to be this complicated. I don't like how they set up their scale because notice the 3.3 value is times 10 to the third. this is all to say it's a little bit confusing, but when you do it, you're going to come up with a value of basically 3.3 times 10. You're going to have this value, the inverse of t, is really going to be something like 0.0033. Units for that, by the way, are Kelvin to the -1. Okay, so this right here, 3.3, really is 0.0033. And the way they did this was I kind of understand, because that's kind of a hard number to put there. What they did is they went ahead and packed it up this way. Okay? All right. Very good. Okay, so we need to unpack that 0.0033. And you already see the line there, the thing down here. So to unpack it, basically we have to take the inverse of that temperature. Now this talks you through it or whatever, but I mentioned kind of my growliness to the units, how they did their plot. If you simply forget all that stuff, if you simply take 1 over 0.0033, you should get 303. Let's try it. My calculator's dying, but yes, I know. So, does that make sense? Other than just the silly complications of the kind of the x-axis being kind of silly. Okay, so that's the temperature that you would have an equilibrium vapor pressure of 116, okay, millimeters of mercury. Any questions?
How did you get 3.3? You did the 1 divided by t times 10 to the third.
See, the reason my answer key does this is I got this off of their graph. At the bottom of that little graph, it says 1 over t times 10 to the third is equal to the number we picked up.
I thought the number was 3.3. Are you just adding a
Oh,
zero?
I see. Yeah, just adding a 0.
Okay.
Very good. I think because it was right on the mark. I see what you're saying. Yeah. Very good. Okay. Very good. So far, so good. Clausius Clapeyron plots. We're going to make one here in a minute. Okay, so again, along the y-axis is the natural log of the vapor pressure, and along the x-axis is going to be the inverse of the temperature. The temperature has to be in units of Kelvin. What do I have next? So let's focus on the slope part. That m, the slope of your line, is going to be equal to negative heat of vaporization over r. Let's kind of see how we could use that to our advantage. Where the value of r you're going to use is that thermodynamic value of r, is the way I think of it, 0.00831 kilojoules per mole Kelvin. So factor label-wise, if you have factor label-wise, this is going to give you heat of vaporization in terms of kilojoules per mole. Because your slope is delta y over delta x, and there are no units for your y, and your x are actually units of inverse Kelvin. So it all works out. So let's pick on nitric acid, and actually you guys are going to do a plot for Monday. So in my hints for the homework that you're going to do for Monday, I say see nitric acid. All right. So somebody ran this, goodness, 1, 2, 3, 4, 5, 6, 7 times. Okay. I think you guys are only going to run it 5 on Thursday. It won't be nitric acid either. And what they did for each one of those temperatures is they paused and got a fix on the equilibrium vapor pressure, which, not so surprising, increased with temperature, right? Okay, cool. So then with that raw data, slide slides here that said that they basically used Logger Pro, and you can make a calculated column, so we can go ahead and make the manipulations we need, so like the natural log of pressure, convert the Celsius to Kelvin, and take the inverse. Okay, so you make your, if we're after the, well, I guess this is it. If we're after the heat of vaporization, okay, we make the Clausius Clapeyron plot. We evaluate, I'm sorry. I knew I was going to say. This, is that top one a Clausius Clapeyron plot? No. But you're going to see it here in a minute. This one right here, this top one, is actually not the natural log of the vapor pressure, but this is just the equilibrium vapor pressure, and not the inverse of the absolute temperature, but this is just T. So it's just a nice little plot. Okay, this one is your Clausius Clapeyron plot. ln of P over 1 over T. And actually, the coup de grace is, actually this is where we're going to use the slope to go ahead and come up with M is equal to negative heat of vaporization over R. From that one. All right. So this is the first plot. Okay, this is just equilibrium vapor pressure versus temperature. Not linear, not so surprising. People who find these relationships are just like, really? I wonder if it's two guys, Clausius and Clapeyron. Must be. Okay. So that one, not straight, but interesting. So getting ready to go ahead and manipulate those 7 points into something that we can plot for our Clausius Clapeyron plot. The raw data is temperature and vapor pressure. Temperature's in Celsius degrees. So let's go ahead and fix the temperature first. We can have Logger Pro go ahead and add 273.15 degrees units to go ahead and get it to Kelvin. Okay, and then we can actually go ahead and have Logger Pro take 1 divided by that new column. And that's actually now ready for the x-axis. And then one more kind of fix. Basically, we need to take the raw equilibrium vapor pressure and take the natural log of it. And that's what this is. Okay, this last column came from the second column. Raw data, okay, calculated. So that's going to go along our y-axis. And we're ready. So we just need to snag these and see what we got. Okay, so there's their points. Pretty good. It's like a straight line. And of course, Logger Pro will give us that little information. Correlation coefficient near 1 or negative 1. If it's a negative slope, looks great. The slope, it's, sorry, near 1 or negative 1 if it's a, yeah, negative slope. The slope itself, actually, that I don't know if Logger Pro does this now or not. This actually is, I think, graphical analysis. But do you guys buy this, that actually this is negative 4.64 times 10 to the third? Okay, that's what that means. Okay with that? Okay, so there's our slope. Woohoo! Okay, so that 4.64 times 10 to the third actually is 4,640. Negative 4,640 because it had a negative with the coefficient. Okay. Let me go back just one. And I need to emphasize this coming up. But slope, even slope, variable m, Logger Pro spits it back to us, but it's always change in y, rise, over change in x, run, right? Okay. And so slope actually does have units. But the units of this over here, the natural log, those units are no units. Okay. And the units of the inverse of the absolute temperature, I think I've already said, the units actually down here are k to the minus 1. So basically, for slope units, we have no units, I'll put kind of a blank, divided by k to the minus 1. And we've kind of talked about how you go ahead and get rid of that stuff down here. Basically, if you want to bring it up, you can take the exponent times negative 1, right? So actually, this resolves to units of Kelvin. So that's why on the next slide, the units of the 4,640 is units of Kelvin. So actually, that's kind of a nice thing. Okay, so for nitric acid then, we are prepared to go ahead and knock out the heat of vaporization. But let's go ahead and according to the Clausius Clapeyron equation, the slope is equal to negative heat of vaporization over R. Rearranging, solving for heat of vaporization, it looks something like this. However you want to do that. I usually crisscross multiply. Like M times R is equal to negative heat of vaporization. And then if I want to get heat of vaporization by itself, I have to multiply both sides by -1. So this is what we're going to do with nitric acid. We're going to plug in the slope, and we're going to plug in the R value, and voila, with its units. So here we go. You see the slope, 6,460 Kelvin. Did I say that right? See the slope, 4,640 Kelvin. Goodness. The value of R, 0.00831. Units of R, kilojoules per mole Kelvin. So do you see where the units of Kelvin cancel? A love factor label. And the units that we're left with are kilojoules per mole. So how are we going to round this? 3 sig figs. Dun, 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 dun. Heat of vaporization for nitric acid then would be 38.6 kilojoules per mole. Not bad. Any questions? So there's all sorts of things you can do with a Clausius Clapeyron plot. Find your way around. Okay. So we're going to revisit that Clausius Clapeyron plot, and we're going to knock out what is the temperature that nitric acid would boil at normally. And by definition, I don't know if I brought it in here. Yeah. This actually is an old slide. You had it back in the same part 3. By definition, the normal boiling point temperature is, or the boiling point temperature in general, forget the normal, is when the equilibrium vapor pressure is equal to the pressure of the atmosphere, called the external pressure of the atmosphere. Equilibrium vapor pressure, they're equal. And under normal conditions, our atmosphere runs 760. Okay, so basically, normal boiling point temperature is the temperature at which the equilibrium vapor pressure is 760. Okay, the normal boiling point temperature is the temperature at which the equilibrium vapor pressure is 760 millimeters mercury. Yeah, this is an old one. Okay, so here's what we're going to do then. Okay, basically, what we need to use that Clausius Clapeyron plot for nitric acid. And we need to turn our attention to the y-axis that has the natural log of pressures. And actually, this will be an extrapolation instead of an interpolation. But we can't pick off 760 millimeters mercury on our Clausius Clapeyron plot, right? We're going to take the natural log of that and then look for it on our plot. And that's exactly what we're going to do. So the natural log of 760, now this is an example of where I get to tell you, and we'll be doing more with logs, why I get to tell you that actually this has 3 sig figs. And actually, after you apply the log of something, the number of sig figs comes after the decimal. SF after decimal. Because the first 6 is 6.63. The first 6 is kind of giving you kind of like a magnitude statement about the log that you just came up with. So 3 sig figs, 3 sig figs. So anyway, 6.633 is what we got to go find on our plot. But if you go to find it, the problem is you're going to see that actually it's above the points of data that we collected. Okay, so that's why it's called extrapolation instead of interpolation. Interpolation means it's kind of nested in your points. Extrapolation means here's the points and we got to go out. Not too far, but just a little bit. So that circle there is your 6.63. Okay, that's about as close as I could get. Okay. So that little circle would be the corresponding 760 millimeters of mercury, but it's the natural log. Okay. So then we get to see where it intersects down here. Now, Logger Pro and graphical analysis, notice there is this feature that I can't remember. It's like Analyze or something. You can basically take your mouse and run it around. So when we kind of put the crosshairs there, it went ahead and told me what this little temperature is. It's hard to pick off, but it told me that's 0.00281. That's the inverse temperature. Okay? None of that other stuff. So all we got to do basically is take 1 over that to get the real Kelvin temperature. And we're done. Okay? Does that work? Okay. So that's what's done right here. So the x-axis value for the inverse of the temperature is 0.00281. Picked it off of graphical analysis or Logger Pro. So to knock out what the real temperature is, we got to take 1 over that. Again, yeah, just 3 sig figs for this. And I can see that this really should be right? So put it in your calculator and you get 356 Kelvin. So that's the normal boiling point of nitric acid. Kind of fun. I personally wouldn't want to boil nitric acid, but and you don't do well with nitric acid. Okay, very good. And if somebody said, hey, that's all well and good, but I don't do Kelvin, do something more like a normal temperature on the metric scale still, that would be Celsius. So we can back that down to Celsius temperature by subtracting 273.
Is this how our homework's going to be like this problem?
Some of your homework's going to be like that. Mm-hmm. The homework, there's like an assortment of problems this time.
Okay, so it's different.
Yeah, but yes. Yep. All right. So from nitric acid to diethyl ether, okay? Now this is this is a classic. Let's just say you went to the lab, okay, and you're like, I am so not going to gather five ordered pairs of pressure and temperature, pressure and temperature, and make a plot and all that. Instead, I just did it twice. I just did 2 runs, okay? But basically the same information is there for those 2 runs. You see the equilibrium vapor pressure and the temperature, equilibrium vapor pressure and the temperature. Okay, 2 runs. And my advice to you would be to still kind of think of this as kind of plotting those 2 points and kind of how do you go about getting the slope of the line. The question at hand is to come up with the heat of vaporization based on those 2 points. And you only need 2 points to define a line. And straight lines have a slope. Okay. So there's a couple different ways to skin to make this skin this cat. And you'll see me on my answer keys probably do a little bit of both. But we'll stick with the slides this time. Okay, so right off the bat, kind of what I do here with the first and the second point is to fix the temperature. I fix the temperature from Celsius to Kelvin because I know I've got to do that. And I'll just go ahead and, like I haven't drawn enough of these today. Like, oh my gosh, is she ever going to stop drawing this? Natural log of pressure, okay, equilibrium pressure, inverse of the temperature, okay. negative slope. 0.1 or 2, 0.1 or 2, okay? I don't know. I guess we better pick. I never know. Okay? The slope of the line is change in y over change in x, okay? Change in means subtraction, okay? So basically, and for some reason, it's always, you go with the second point, and from that you subtract the first point. Oops. Instead of p, I need to say the natural log of p. Yeah, it would have been y2 minus y1, but I'm going to go natural log of p2 minus the natural log of p1. Okay, very good. Then, on the bottom, what will it look like?
T.
1 over T2 minus 1 over T1? Does that seem reasonable? Then one more thing, and I'll go ahead and clean this up, it's on the slide. I'm not going to do anything with the bottom, 1 over T2 minus 1 over T1. But there are some really cool properties of logs, whether it's the natural log or the log base 10, LOG. If you have a subtraction like this, actually that's the same thing as taking them out and putting this in the numerator and this in the denominator and taking the natural log of that ratio. So the natural log of P2 minus the natural log of P1 is equal to just a single log, P2 over P1. Whew. Okay. So actually what you wrote down there is right here. Does that work? All right. Okay, are we ready then? And that's all equal to the slope. So that's M, and M is equal to negative heat of vaporization over R. Okay? All right. So let's look at the points that we have. That's why we went ahead and got the temperature in units of Kelvin. So it's the natural log of 534 over 57.0 divided by 1 over 298.2 Kelvin minus 1 over 250.4 Kelvin. This is where it's really easy for me. My eyes start to get buggy when I'm like, well, which point goes with which? And I'm like, ah. So, but you might want to do that a few times in your calculator. Rounding to 3 sig figs, I think, ultimately. Notice that I have an intermediate value there. I think I would have gone with 3 sig figs. But this intermediate thing, okay, when the dust finally settles, you end up with negative 3,494 Kelvin. And that's just the slope. So we haven't found the heat of vaporization yet. You're like, really? Just to kind of emphasize what our next step is, down here at the bottom, say M is equal to negative delta H VAP over R, which is equal to that. And we know R, so I'm going to go ahead and knock this out. Okay, we said that if we're after the heat of vaporization, which we are, and if we have M, which we do, we can actually get to the heat of vaporization by taking negative 1 times the slope we got times R. Okay, and so this is what this looks like finally. negative 1, that's the slope, negative 3,494 Kelvin times R, which is 0.00831 kilojoules per mole Kelvin. So that's how we got to the heat of vaporization from just 2 points.
No, I'm getting funky numbers.
Yeah, no, we will be definitely doing more with logs, so. Did you get that?
Woohoo! Wait, so you took this, the log of the points, and then you got equals to this?
The log of that ratio, I think so.
Equals this?
Mhm.
Why not the final number?
That's okay. It looks like did you do this down here too?
Yeah.
Good.
Oh,
You just
okay.
didn't do an intermediate, that's
Oh,
perfect.
okay.
Yeah,
I was
she
like,
just,
oh,
she
man.
just worked it without the in-between. Did it work for you?
Yeah.
Good, all right. So let's take a look at your homework, eh? So where it says graphical analysis, really you're using Logger Pro. Make sure we're all on the same page. I am glad to be able to share some of these hints with you. And I've got it ready just to, in case I get sidetracked, I can just click it. It's ready to send to you guys. Okay. But some of them are very similar to what we did today in class. Last part. Okay. So this is the first question, and it picks on, actually two substances. In A, it's aniline, and in B, it's diethyl ether. And it says, use the data in this figure to estimate the normal boiling point of aniline. So this is kind of like what we did. Basically, normal boiling point means the temperature at which the equilibrium vapor pressure is 760. So you have to convert 760 to something from the Clausius Clapeyron plot. So take the natural log of that, like we did before, and I have a dot, dot, dot. I don't know what that is. And so then, as you know, basically then you find where it intersects with the line, you come down, you pick this off. You're going to have to kind of mess with the, the temperature kind of being balled up like that. But ultimately, you'll take the inverse of that temperature to get the Kelvin. All right, so that was not too bad. For the vapor pressure of diethyl ether, that's the red line, right? Okay, oops, we already did that. So what you do is they give you that temperature, and they want to know what the equilibrium vapor pressure is. So you take that temperature, 25, and you have to convert it to Kelvin. Take the inverse of it and find it on here, okay? And then find it where it intersects. You'll go up where it intersects the red line, and then go over here, okay? Now, we didn't do one of these, so I'm glad to kind of show you this. Okay, once you find this value over here, okay, the last little bit is, and we could try an example, or I might just turn you loose. To basically get to that P, what you're going to have to do is undo the natural log. To undo the natural log, you're going to find the E key, the little E key, okay, E to the caret, okay, and you're going to raise it to whatever value you find along the y-axis. We could play around with that. We could go back and forth. So if you take the, what did we say the natural log of 760 is?
6.63.
6.630? Thank you. Okay, so then basically to undo that, if we take E, try this, E raised to the 6.630 power, you should get 760. Isn't that fun?
Yeah.
Any questions? E raised to that.
If you replace your 0 with a 3, I told you wrong, it comes out closer to 760.
Okay, what do I do?
Replace your 0 with a 3,
Put a 3 there?
and it comes out to be 759.75.
Very good. Well, I appreciate that. Okay, so that's how you do that. The next one looks like this, where we're dealing with a cyclohexanol. And it's the one like we just did. Basically, they give you 2 data points, okay? And this is like what we did here. Okay, so you're after the heat of vaporization. So it looks icky, but it's really not too bad. Okay? I bet you'll do fine, and I'll go ahead and push these out there. 0.1, 0.2. And what I used to do was really be careful, basically kind of draw my and then I would take those and take the delta y over the delta x to get the slope, but it's the same diff. Okay. Okay. The next one. Yeah. This is one where I actually wanted to, I was running low on time, so I just dug out my answer key, because I'm like, what other information? So we're dealing with methanol or methyl alcohol. It's the same thing. And basically it alludes to using other information from your text. That other information from your text is on table 12.3, and it's the heat of vaporization of methanol. Okay? So I went ahead and told you what it is. You can double check though. So basically what the Clausius Clapeyron equation says, well, let me show you what this is. So it goes on to give you only 1 point. It gives you one of your 2 points. Okay, I know. Okay, it gives you the temperature, 5 degrees, and equilibrium vapor pressure. And then it says, at what temperature does the stuff boil? You're like, what the heck? Well, by definition, it boils. Its normal boiling point is when its equilibrium vapor pressure is 760. So that's where that comes in. Okay, and this is the unknown. Okay? Yeah, I know. So then basically we have the negative heat of vaporization over R is equal to this mess, okay? And we know all of that stuff, and we know everything but T2. Okay? That's it. That's your hint. The last one is kind of goes back to kind of more what we did with nitric acid. I say, see the nitric acid, okay? The 5 points are just like the ordered pairs, temperature, pressure, okay? And so this is where you're going to want to use Logger Pro to enter those 5 points. I'd really, this is going to help you for Thursday's lab. Go ahead and have it, convert it to Kelvin, inverse temperature, will make Logger Pro do the work here, the natural log of the equilibrium vapor pressure. This is the plot that you're going to draw, okay? And then the 2 things you're supposed to do, first you're supposed to find its normal boiling point temperature, kind of like we did with nitric acid. So you're going to interpolate or extrapolate on here, okay, come down, and what's that temperature. And the second thing is to go ahead and use the slope and get the heat of vaporization.
So we need to do all that and print it out.
Yes.
Yeah.
And we might get snowed in on Monday.
Are we really supposed to get that much snow?
6 inches or something.
Is it 6? Okay.
It was 6 to 8.
Yay. I
And then
thought it was
there's-
going to be a little drizzle.
Or they just changed it to 6.
That's super duper.
So I don't know. Maybe not. Maybe we'll even get more than that.
I know.
No.
When's the snowstorm?